All right, so to continue where we left off using Xcode instruments, so last time we were able to identify the error, identify the busy main thread. So now we're gonna pretty much analyze what might be causing the issue there. So what we start off by is saying the title for the section is analyzing main thread activity. So we say knowing what's happening on the main thread is essential to understanding hangs, especially for busy main thread hangs, which is what we are experiencing right now. And again, just to give a visual for what that might be, is that this is our Swift UI app, and when we click on collection, you'll notice that we don't get navigated immediately. It's basically a huge delay, and that's our hang. And we're able to see that in our instruments last time here. So this is the hang that takes place whenever we click on collection. We have this huge wait time of 5.91 seconds, which is a horrible UI experience, UI UX experience. So let's open. So this is instruments again, and then let's just scroll down. If you didn't follow the previous stream, just download this file right here. This is provided by Apple. You'll be able to be right in the same position as we are with this project. So next section 1, use a profile view to understand main thread work. So and it says, knowing that the cause of the hang is a busy main thread, the next step is to investigate what work is happening on the main thread so you can develop a strategy to reduce that work. So how we can tell too visually is that we're using the time profiler instrument, and then from the previous stream we found out that like whenever you see the bar graph like this, as in like it's heavy usage, that's pretty much the CPU doing a whole bunch of work, and we see that some points even pass 100%. So we learned that that might take up our entire core in the previous stream. So let's just jump down to here. And so the issue we're having is a busy main thread, but you could also have a block main thread, where that would be a huge gap in between inside this trace right here. All right. So it says, so far you've examined the track area in instruments at the top of the window. Focus on the bottom part of the document window. So I guess for this portion here, for section 1, we're going to be focusing heavily on this bottom part here. It says this is the detail in the area. Its contents change based on what you selected in the track area. So let's see if we can just test that out. So right now we're on profile. So each of these are a different track. And it says the bottom portion here will change based on what we select. So let's select time profiler, and we see this bottom set of operations. For points of interest, you don't see anything. Thermal state, one increment here, one element here. And for hangs, we see something. So it looks like every track gives us updates the bottom portion differently. Okay, so by default, it says documents created from the time profiler template display the profile detail view in the detail area whenever a track with CPU information is selected. So let's click on time profiler again. So by default, documents time profiler template display the profile detail view in the detail area whenever a track with CPU usage information is selected. Okay, so this uses CPU usage. So when we click that, we see all of this information like they mentioned. And then it says the profile view shows a call tree of all functions executed during the selected time on the left. All right, so let's look at this portion first. So it says the profile view shows a call tree, all functions executed. Profile view. Profile view. Oh, this entire thing. And it says the profile view shows a call tree of all functions. So these are some of the functions that were called. Executed during the time on the left. This one. And then and a heavier stack trace view in the extended detail area on the right. So and they pretty much have it here. They show it right here. So this is a track area. So just refer to this. This is the track area. And now our detail area which is the heaviest stack trace area. Maximize this a bit. Yeah. And then here is our detail area, which represents our heaviest stack trace. Scroll down just to look through this a bit. Oh, and it automatically links with the other area over here. So this is the extended detail area, and this is our call tree area. Okay. All right. So the next thing is focus on the call tree view. So this would be this area we have here. And it says click the disclosure triangle in the outline view next. All right. Okay. Here. Okay. To expand its nodes, repeat to expand a few more child nodes. So we're gonna keep opening these, expanding them, because it says click the disclosure triangle in the outline view next to start to expand its child's nodes. Run it down for a couple of them. So start underscore sim main static dot app. Then we have run app here and closure. Repeat to extend a few more. I don't know how far they want us to go, so let's just go like probably 2 or 3 more. And then at the top of an app's call stack, the first couple of frames often a single child node. Okay. And then it said this is because the corresponding function only called a single relevant function. You often have to click many times to arrive at an interesting point in the call tree. Okay, so they're saying that we'd have to keep clicking all the way down to get to like actually where in the code we would have this hang happening. It says at the top of an app's call stack, which is here, the first couple of frames often only have a single child node. We see that at first, and we kept going down. This is because the corresponding function only called a single relevant function. And then you often have to click many times to arrive at an interesting point in the call tree. Yeah, we see that. So let's watch a replay here. You see they click on start, they click on main, they keep clicking, pretty much what we were doing. Going all the way down till they reach run app. Alright, so option click on a disclosure triangle to expand all call tree levels until there is more than one child node. Option click. Okay. Test this. Okay. So opens all of them and we can scroll all the way down. Last one. Oh, this can scroll horizontally. It goes for really far down. Okay. Looks like there's some okay. Alright. So it says the contents of the profile detail view expand on your selection in the track area. Now it says select a different time range by clicking and dragging in track area. In the track area and observe how the detail view updates. Then select different thread tracks. The detail view updates again. Alright, so we have to go back up to our track area, which is up here. And we can be sure of that because pretty much you said it here on this diagram. This is the track area. This side here is a detail area. Also the extended detail area, but pretty much a detail area. And then all of this is our call tree. And then over here is our profile detail view with the weights. Let's scroll back down again. And all right, we'll just replay it when it finishes. All right, so it's the first thing it says is select a different time range by clicking and dragging in the track area. and observe how the detail view updates on the hero will update. So when we change like the time fill to the time range in here, our detail view will update here. Let's do that first. Let's look at those. Okay, so you can drag it to. So let's try that. Now what's the next thing? It says detail view. Then select different thread tracks. Then select different thread tracks. The detail view updates again. So each time you're selecting a different track, detail view is just going to keep updating to match that track. Okay. And say the call tree always shows only functions that executed on the selected thread. During the selected time range and updates based on your selection. So it's saying that then again, the call tree always shows only functions that executed on the selected thread. Let's open up our option, so our process, so we can see all our threads here. And we did this previously in other stream, that's why we know we can do this. Okay. And then select different thread tracks. Select a different one, both of these. We see these update, but what we want to do is add a new filter, time range filter. And let's play this one more. Kind of hover over it and then it kind of sets it. Then set my range to this. Now we're only focusing on this range, and I can click on different threads to see what was happening during that time range. Yeah, that's kind of sick. All right, so then select different thread tracks. The view updates again. Call tree always shows only functions that executed on the selected thread during the selected time range and updates based on your selection. Okay, so it's a way how we can see what each thread, what a specific thread was doing during a specific time range that we recorded. Yeah. So if we wanted to see what the thread was doing, say when we just launched the app, we could limit the time range to here, and then we could check it. Or basically, if we want to see earlier, we'd probably do it earlier. Cool. Next thing is select the main thread track and the time range of the hang interval. Let's select the main thread track here. The hang interval again. And the time range of the hang interval is pretty much right here. They're handling. I wonder if they're going to use specific range. Yeah, they did that. So they did set in specific range. So let's click this, click our main thread, and then let's go over to the track with our hangs here, and then we're going to click set inspection range, and then it just kind of zooms in and focuses on this area. So I guess we're going to zoom. Yeah, well, shows it like this and dims the sides. All right, so be sure to combine both the track selection and the time filter, because for the track section and the time filter, because you want to focus on what's happening on the main thread during the hang. What happens before or after the hang usually isn't relevant, and neither is what happened on the threads. So they want us to use a time filter here as well. Just click this. Click on this. Set the specific range. Then dragging this. Let's just play the replay. Range. That's it. Yeah, so we don't even have to do that. We could just do set specific range, because it's still doing the same thing. It's just focusing the filter, the time range filter. All right, so what happens before or after the hang usually isn't relevant. Nice. And let's focus on main thread here. All right, so section 2, identify relevant functions. So even when using option click, there are a lot of frames to shift through in the call. Inside our call tree here, when we do option, there's still a bunch of frames to click through. Oh, sorry, this is our call tree down here. Then it says the heaviest stack trace view summarizes the information in the call tree even further and can often lead you to relevant stack frame. This area, so I guess they're saying instead of just relying on using this where we have to keep pretty much using the disclosure, keep tapping that arrow, we can actually use this instead. So I guess it's just the same thing, just like a different view. So let's see. All right, so even when using option click, what we did when we could see option click, and it opens all of them going all the way down. It's still a lot of frames to sift through in the call tree. The heaviest stack trace view summarizes the information in the call tree. Call tree further and can often lead you to relevant stack frames more quickly. Okay, so we can find what the issue is if we use this file. In this section, you will use it to find out where the main thread spends its time during the hang. Okay, that's exactly what we're pretty much trying to find. So yeah, look at the heaviest stack trace view in the extended detail on the view on the right, which is this right here. And it said the heaviest stack trace shows a summary of the call tree. Heaviest stack trace shows a summary of and uses heuristics to identify relevant frames without you having to sift through the whole call tree, which often contains thousands of nodes. So it's a better way how to find what the problem is for instead of going through all of these nodes. We can just look through the heaviest stack tree. Yeah. All right. If the heaviest stack trace view isn't visible by default, you can show it by clicking the small button at the far right of the divider view. Guess this. Click this just to see what they're replay. Oh, so if you want to hide it or show it to just do it. I wonder what this one is. Oh, I guess you can show our stack tree or call tree in different ways. Let's switch back to our call tree, our heaviest stack trace, and our track view or something. All right, so instead of the whole call tree, the heaviest stack trace only shows a single call stack. Stack shown in the heaviest stack trace is computed by starting at the root nodes and picking the ones with the heaviest weight. That is, again, instead of the whole call tree, the heaviest stack trace only shows a single call stack. The stack shown in the heaviest stack trace is computed by starting at the root nodes and picking the one with the heaviest weight. Whichever one is taking the longest or the heaviest weight. Then for each child of the last chosen node, it picks the one with the heaviest weight again, and recursively continues until reaching a leaf node. So I guess it keeps finding the heaviest nodes and it adds them in here. So this is because that's why these are white highlighted here. And then the rest of these are pretty much what's the weight here. So the weight for this is 5.13 seconds. And then the weight for this one is 5.13 seconds. After that, a couple of these are 5.13 seconds. All right, then for each child of the last chosen node, it picks the one with the highest weight again and recursively until reaching a leaf node. Might have to reread that a couple times, but yeah. All right, there is one additional constraint. Final heaviest stack trace must contain at least one node that's currently selected in the call tree. All right, so there is one additional constraint. The final heaviest stack trace must contain at least one node that's currently selected in the call tree, if any. This way, it gives a good summary of where your app spends most time. while also taking the current selection. Let's look at a replay. Oh, that's not the replay one. I wish they gave us a replay for that. This was a lot to digest. We could throw this in the chat GPT and see if it explains it maybe a little bit better. So let's try that. So little command C. We're just going to open chat GPT. And we're going to say, explain this from see what it can do. All the possible paths are up to call tree. It will pass the. This is what the heaviest stack trace does. Instead of showing all the possible path your app took, whole call tree, it focuses on path, the heaviest one. And it starts at the top, the root, and picks the part of the code that took the most time. It starts here, and then it looks for the next heaviest part. And then it says, starts at the top of the root. Then for each step down the tree, the child nodes, keeps picking the heaviest part until it reaches the end. So it gets the heaviest part at one point, and then it keeps going down, and then it grabs the next heaviest, and then it keeps going down. I guess it's comparing all the other nodes and grabbing the heaviest within those sets of nodes. If you selected a specific part, let me zoom in here. Yeah, sorry about that. Let me zoom in some more. It said if you selected a specific part of the call tree, it makes sure the heaviest stack trace includes the part somewhere in the path. Okay. And this gives you a quick way to see where your app spends time and how to like following the most time consuming route through your app, helping you performance bottlenecks. Okay, all right. So that was just explaining all the heaviest stack trace. So sometimes you gotta chat GPT to get some more detail. All right, so the next thing is because even a single stack can be hundreds of frames. So any of these could be maybe 100 frames. Instrument shows an abbreviated stack by default and attempts to highlight potential interesting frames. Just still the same. Okay. All right, so because even a single stack can have hundreds of frames deep, instrument shows an abbreviated stack by default, attempts to highlight interesting frames. So it highlights which one that we might be interested in using. And then from the visible function names, you can already tell that something related to image processing is taking a lot of time. All right, so where we see? Right here, I guess. Static image viewer app. Just pushes us to this part of this. Let's just open back instruments. So click this back. From the visible function names, you can already tell that something related to processing is taking a lot of time. However, the collapse stat doesn't reveal the whole story. None of your code shows up in this stack, so you can tell which part of your code, part of your app calls these functions. Yeah, so I'm not seeing any other parts of our code actually show up in here. We don't know where in our code. It says click the button in the top right to show all of the frames in the heaviest stack trace. Scroll up here. We're just looking at some of them. Oh, but this is why they're saying it. So this has something to do related to that. So PNG read, okay, and then to all of them. All right. Click on this. Yeah, to hide it, I see. Okay. In the abbreviated view, Instrument shows only groups of frames where the CPU usage between two frames change significantly. Oh, okay. This usually means that the first function in the group doesn't call another function. Instead, it either calls multiple functions at each significant, or the function body itself uses significant. So yeah, we're gonna have to read it again. So in the abbreviated view, instrument shows only groups of frames where the CPU usage between two frames change significantly. I guess there is a huge jump in the CPU usage. Say if we're moving from 20 to 100 or something like that. And then it said this usually means that the first function in a group doesn't call another function. Instead, it either calls multiple functions that each significant amount of CPU time, or the function body itself uses a significant time instead of just. Anyways, I feel like we could give this to ChatGPT too, but let's just. So it said these points in a call tree are often good starting points for an investigation, which is why instruments marks them with a small step icon via stack. In the abbreviated state, these frames are as well as their direct callee with the CPU usage remain visible. However, sometimes you need to look at the whole stack to find what you are looking for. There is another piece of information in the heaviest stack trace that is off. Okay, so step 3. Notice that some function names in the heaviest stack trace are in the default text color while others are in gray. This, and then let's look at. Yeah, this is in white, and then I see these in gray, and this is in white, this is in white. Dimension. Weight on frame, insorted, dimension, symbol name, and then binary of symbol. It says if instrument has more information about original source code for a function, it displays the function in the default text color. So if instrument has more information about original source code of a function, it displays the function in the default. So if it has more info about some function that we worked on, it will show it as white versus it will show it as gray. All right. So I guess we need to really focus on the functions that are like highlighted in white, our default color. That usually means they are part of the source code Xcode compiled for you and can be changed easily. In this case, imageviewer app.main is in the default text color as the compiler generates it from the imageviewer app structure. So yeah, that's why this one is in white. And then main right here, it is in white too. Static view, image view, what is this? It pushes us to, let's jump back to instrument. All right. And then it says in this, I know it says image viewer app.main, which is this right here. Yeah. Is a generic entry point for your app. Guess that is the same place as this. And that might be why when we clicked on instruments, let's go to instrument. When we clicked on it here, it kind of just sent us back to this screen, which is like pretty much our entry point into the app when you're using SwiftUI. Instead, look for other frames from your app in the heaviest stack trace to understand what your app is doing during that hang. Open back up instruments. And it says is a generic entry point for your app. So this is where the app pretty much starts up all that logic that we just saw in the SwiftUI view. And it says instead, so don't bother with wasting time looking in there. Instead, look for other frames from your app in the heaviest stack trace the other frames that we might have. So maybe this one. Do we have any other ones highlighted in one? Oh yeah, we do. Thumbnail view dot body, thumb view dot image view, thumb by. Let's tap this, and it pushes us to a different SwiftUI view. Okay, so these are pretty heavy. They have a heavy weight. So 5 seconds, 5 seconds, and that's pretty similar to what our hang was saying. So 5.1.91 seconds, really similar. So this could be what's causing it. 5 point next. This right here, which is pretty much our entry point. So we can ignore this. We can ignore this, and let's scroll down. We can ignore this because it's just entry point. See, if I click on it, it just sends me to app main. So if I jump back to instruments and I scroll down, I'm going to look for the next one that's white. So it's these right here. And it's a couple of them. So let me click on this one first. And it pushes me to the thumbnail view. So I guess we're having some, this might be where we're having some issue. And then let's look at the other one. Thumbnail view 23. Let's click on this. Okay, so it's definitely something happening in thumbnail view. So it says scroll down in the heaviest stack trace and find a function called or other symbol from the image viewer binary. Look for functions in their default text color and ignore the gray ones. Yeah, we just did that. We looked up on these. And so you can move the pointer. Oh, so this is actually the replay. They scrolled, and they got to the same point. Thumbnail view, body, thumbnail view, image view. Okay. And now it says you can move the pointer over such a frame in default color to display the file and line number that the function appears in. And then click the file name to open that file in Xcode. Just did that, but do it again. This is one of them. This is a different file. So it's like three potential places that we might need to update, I'm guessing. It might be 3 potential places I might need to update. So open back instruments. And it says the first function of your app code that's in the heaviest stack trace is thumbnail view, not body, which is this right here. This is select the thumbnail view, not body getter from row in the heaviest stack trace. When you select a row in the heaviest stack trace, the call tree automatically scrolls to and highlight corresponding row. So if when I click this, it's gonna, our call tree over here kind of just dates and aligns to it. Where we click, so if I click, okay, so they're right after each other, so that's how it's this one. Oh, but you see where it says when you select a row in the heaviest stack trace, the call tree automatically scrolls and highlights the corresponding row. And we saw that in very deep stack station like high, and you may need to scroll horizontally to reveal the name of. Oh, that's why we weren't seeing. Wondering also. But if you see it and you just see this right here, you're not seeing any information. You actually have to horizontally scroll. Now we see the name of the function because we're so deep in the stack. All right, so all right, next thing is step 6. It says examine the weight column. That is this right here. In the call tree for the thumbnail view dot body getter dot getter row. It shows that over 98% of the CPU time on the selected thread during the selected time is spent running the body getter of gets all these. For us, it's 97%. For them, it's 98.3. So I'm looking thumbnail view getter. Yeah, we're doing 97.7%. I'll say it's pretty close to 98%. They probably just rounded up. It shows that over 98% of the time on the thread It shows that for 90% CPU selected thread during the select time is spent running the body getter of the view and its calling. And that's just a SwiftUI view and it's running, taking that long. Previously, you selected the main thread in the track area, okay, and you set the time filter to only cover the hang duration. Yeah. This means the data displayed in the call tree view only covers the CPU spent by the main thread during the hang. So we made it that we're filtering, we're only focusing on the time frame when the hang occurred. And previously selected the main thread, but this means that the data displayed in the call tree view only covers the CPU time spent by the main thread during the hang. Overall, the main thread spends 4.5 seconds during the body getter. Almost complete explains the overall hang duration. Yeah, because it's taking my time, it's 5.1 seconds. Okay, so we're able to analyze this section, and now we're back to now we're at the summary. So it says, you now know that the hangs is the result of a busy main thread, and that it's related to the body getter of thumbnail view. This is the function where a lot of CPU time is spent during the hang, but it isn't necessarily the root cause. So again, we can look at the weight and we see that it's actually 5.1 seconds here. And we can tell from the heaviest stack trace that it is the next point in where we're running that really it pretty much highlighted and saying that that's our code and it's taking an exception a lot of time to actually run. And then we have three of them, so it's this one right here, thumbnail view for the body, and then somewhere in the body we're using thumbnail view, that image view to get the data. And then we have something here we're calling to make a thumbnail. So let's click on this and let's see where this puts. This should put us inside our. Okay. All right, so it says, you now know that the hang is the result of a busy main thread. That means you're doing too much work on the main thread and it's might use up too much of the CPU process. And that is related to the body getter of thumbnail view. This is the function where a lot of CPU time is spent during the hang, but it isn't necessarily the root cause. If you know your app's code well, just know where a lot of the time is spent may already tell you all you need to know how to make a fix. So if you know your code, like you wrote an app and you know that there are certain parts where you're maybe downloading like a huge document or using an API that takes a lot of time, you might already know that if you're seeing some hang, it might be some cleaning up that you might need to do there, or just some updates that are pushing some of the work to a background thread. And then it says, however, apps are complex pieces of technology, often created by many different people. This means that you may need to work on code that you haven't written, or your code interfaces with a framework you're still learning about. This will happen all the time. As long as you're working on any type of team, you're going to be working with other devs. You have to read and understand the code. And so in this case, you need to gather more information, understand what exactly is happening. In the next part, you will learn pretty much how to interpret information provided by Time Profiler, what Time Profiler can tell you, and what you need to know to fix the issue on the app's main thread. After that, you'll use instruments again to record more detailed data. So for this, I guess we just analyzed it, kind of understand where exactly in the app is using so much CPU usage, or maybe even using up more cores. And like we have a better idea of how to understand how that operates. And now for the next one, we're going to basically be using it to determine how frequent we're calling some of these functions. All right, now we know it's some issue related to thumbnail view. Again, we can find it by checking our heaviest stack trace. And we'll see that that's the one that's taking up more than close to 5 seconds, and causing that possible delay with a hang. So in this case, you need to gather more information to understand what exactly is happening. Next part, you'll learn how to interpret information provided by Time Profiler, what Time Profiler can tell you, and what you need to know to fix the issue on the app's main thread. So we're going to be using more Time Profiler. After that, you'll use instruments again to record more detailed data. To save some setup work in the next tutorial, keep your instruments document open, and you can use your iPhone if you want, but using the simulator is fine since this is an issue that it doesn't really affect your processor. This is gonna just be happening, forcing this to happen. So the next thing is we're gonna be handling determining the execution frequency, like I guess how often how often the hang is happening. So learn about the two basic ways to fix hangs and how to decide which one to try. That's it for this portion. If you like this, just definitely like, comment, and subscribe, and we'll talk more about using more Xcode instruments to better understand under hood of all the work that's happening behind under your app, like the performance, how to handle hangs, how to improve them and fix them.